Hello and welcome to week 13 of PUBH 612. Today we will discuss quantitative data analysis and interpretation. This is chapter 14 in your textbook. This week we will be discussing quantitative data analysis, and some of you will have taken biostatistics and epidemiology, and this will be a refresher, while for others it will be an introduction to new material. Overall, I'm not too concerned with you memorizing the differences between chi-square tests and one-way analysis of variance or ANOVA for nominal bi-interval data. However, I want you to be able to select an appropriate measure to capture change in a program, to be able to identify the elements of a persuasive statistical argument, and lastly, to choose a statistical procedure for your level of measurement. First things first, this week we need to talk about data entry and management. If the data were collected on paper, then they're going to need to be transferred into a database or a spreadsheet so that evaluators can conduct statistical analyses. The software that you choose should be based on the user's skill level. For instance, I would love to do an analysis in R, but I don't know how to use that software, so I use SPSS or SAS. And also, you shouldn't underestimate the number of statistical analyses that can be done just using Excel. Overall, you're going to also need a system to track data entry, manage and store documents if needed, and to create backup files. And data cleaning is a critical and rather labor-intensive step that will require you to check data entry for data entry errors, and it will begin with reviewing frequency distributions for all of your variables and look for variables that don't seem reasonable. And if you find something that looks suspicious, you can check if the data were entered incorrectly, or if the response is so unlikely, for example, a respondent saying that they had 500 children, you may consider just tossing that value and classifying the data as NA or missing. Keeping an incorrect value in your data set can change the mean, the standard deviation, and statistical tests later on. And you should also review your data for skip patterns to make sure that if you have a low response rate for some questions, it's not because of something like a skip pattern. Outliers are those variables with reasonable, plausible, but extraordinary values that lie at the extreme ends of the distribution of data. Sources of outliers can be measurement errors, data entry errors, but they could also be unusual but accurate values. And so you must decide whether or not you want to include outliers, and this needs to be done really on a case-by-case basis. Linked data refer to data that results from merging data from more than one source so that a comprehensive set of variables becomes available for subjects in the data set. Examples of uses of linked data are to connect program participant data with outcome data, or to link program outcome data with process data. For example, you may want to look at how many mental health counseling sessions participants received, which would be a process measure, and if it's associated with better mental health outcomes among participants. It can also be used to validate self-reported responses. For example, people may self-report exercising every day, but if you weigh them and there's no change in weight, you may question the validity of their self-reported response and wonder if there's some social desirability bias in your findings. Some caveats to linked data are confidentiality. because you will need unique identifiers for your data so that you can match records without using participants' names, and you need to check your data for accuracy. So how do you measure change? In terms of a program effect evaluation, change is a difference, and it's a relative term and is detected only by comparison. And therefore, the amount of change detected is influenced by what it's compared to. Generally, change is measured in 3 ways, which are shown here. The first is to subtract an initial baseline score before the intervention from a subsequent score after the program. And the term score, which is shown here in the denominator, is a measure of the health outcome. To calculate change using this first formula, you'll need data from only one group, and therefore it is the only option for evaluations which use a one-sample pre-test, post-test design. For each individual, a different score is calculated and averaged across participants. The second equation that you see here is used for data from both a post-test only design, and this is a weak design, so it's very rarely used. And lastly, there is an equation used in 2-group pre-test, post-test designs. And so here you'll have data from an experiment and a control group before and after the intervention. And this formula will give you a more precise measure of change because it's using all of the relevant data. Here are 4 conceptual challenges to quantifying change. The first is the direction of change, and it's important in some public health programs because, for instance, we could want to reduce the incidence of disease in one program, while in another we want to increase healthy behaviors. And so one way to be clear about the direction of the outcome is to use absolute numbers when you report the change. And you can also use words like improvement, which can be used to describe both positive and negative numbers based on your context. Second is the high level of desired outcome at the pretest. And this relates to the diffusion of innovations and how innovations which are at first novel and used by only a handful of people over time become more widespread and common. And when there's a higher prevalence of the desired behavior before the program, it becomes more challenging to increase the prevalence of the health behavior. So sometimes you may want to take into account the initial prevalence of the behavior when you're estimating the effectiveness of the intervention. Other challenges are how we measure the relationship to an outcome objective of target and the relationship of change to an intervention effort. Regarding number 4, the intervention efficiency score can provide insight into the amount of effort required to produce the amount of change observed. Descriptive statistics are also called an exploratory data analysis or univariate analysis. And it measures frequency of occurrence, such as mean, mode, percentages, and dispersion of values. These data are easy to interpret and obtain and can be very powerful when used to explain your findings to stakeholders. Here are some questions that you can answer with descriptive statistics, such as what were the characteristics of program participants and non-participants? How were pre- and post-test scores distributed? What percentage of participants reached the objective target values? And lastly, are the data normally distributed? Regarding whether or not your data are normally distributed, here in Table 14-5, you can see some commonly used parametric and non-parametric statistical tests for comparison, association, and prediction. When interval measures follow the normal distribution curve, Parametric tests, such as difference scores, t-tests, and logistic regression analyses, can be used. However, if your interval and or ratio data are not normally distributed, then non-parametric tests must be used. In case you forgot what we're talking about, normally distributed data are shown here. This is what a graph of normally distributed data would look like. And so we're talking about a bell curve with most of the data clustered in the center. Comparison questions can be asked for both within group or between group comparisons. So for example, the first question, are post-test scores different from pre-tests, could be asked of both within or between group comparisons, while the last question, is one group more likely to have a characteristic than another, can only be asked if you have between group comparisons. Here is a table showing the main types of comparison analyses used by the level of analysis. But remember that this assumes that the variables are at the same level of measurement. While comparisons and descriptive statistics are important, most evaluations want to know if there is an association between the exposure, your intervention, and the outcome of interest. Testing for associations can answer questions like these. Was getting more interventions related to a greater amount of change, or is the amount of change associated with certain participant characteristics? When you're testing for an association and running many correlation analyses, it increases the chance that some pairs will be significantly related. So you should consider adjusting your p-value from 0.05 to 0.01 to avoid a false positive finding. And you also should include moderating and mediating variables if they're in the causal theory. Questions such as these are essentially causal questions. So, how much of an effect did the intervention have? How much more improvement might occur with more intervention? And in order to answer these causal questions, we will need a more robust evaluation design, something such as a quasi-experimental or experimental design. Table 14-10, shown here, summarizes key statistics that can be used to predict future outcomes. In any study, you need to watch out for surprise findings or questionable findings. A spurious finding is one that is incidental to the evaluation question or is an artifact of poorly understood factors. These findings can be discounted as the result of measurement error and random chance. While surprise findings are not related to the evaluation question, but make you stop and think, these may support the health intervention or not, and can lead to further research or making changes to the program or evaluation. When you're interpreting the results of your evaluation, Green and Lewis suggest there are 4 types of errors that can occur. First, the first fallacy of interpretation is equating effectiveness with efficiency. Second is assuming a constant linear rate of progress. Third is assuming that ongoing improvement can be achieved. And 4, understanding the complexity of the change processes. Lastly, ecological fallacy is the assumption that a group characteristic applies to all individuals within that group. So for instance, if a group of employees had an average of a high school education, it doesn't mean that some individuals in that group hadn't gone to college. In summary, the key takeaways for this week are that there are different statistical tests for different research questions and types of data. And you need to be sure to choose wisely and carefully. And be careful when you're interpreting the results of your data to avoid committing something like an ecological fallacy or one of the other fallacies of interpretation. And lastly, like I said at the beginning of the lecture, not all of us will go on to become statisticians, and we don't need to remember all of the details of each of these statistical tests that are shown here in this lecture, but you do need to understand which tests will help you to answer your evaluation or research questions and to interpret the results for stakeholders or be able to use the evidence to make programmatic or policy decisions. Here are some additional internet resources to help you get a better understanding of statistical analyses, particularly quantitative analyses. And please be sure to check Blackboard for any other materials this week.